Recording's rolling. It is Wednesday, May 7th. We're going to do more quantum journals today, and then tomorrow, plan is to finish that final exam review. All right, so quantum journal. Fill you guys in from a few days ago was the last time you guys saw this. So, what are we doing so far with this? So, quantum mechanics, we're looking at the physics of really, really small things like atomic size, what's going on down at the size of the atom. So, first one you guys did was what size are we talking about? Get some context for that. Okay. And then number 2, 3, 4, these were related to each other. All lead up to this photoelectric effect. So what is light? Is light fundamentally wave or particle? Now, by the time 1900 rolled around, for hundreds of years, people had pretty well established that light was a wave, because you can have a card, you cut a couple of slits in the card, shine a light through, creates an interference pattern on the back wall. Only waves do that, so light has wave properties, light must be a wave. Okay. But then there's this photoelectric experiment. So Heinrich Hertz, 1887. Say if you're trying to capture energy on a solar panel, so kind of related to that, you shine a red light, which has low frequency, long wavelength, and maybe you're not gathering any energy. So okay, so I just turn up the intensity, but you still get nothing. Okay? But then if you change the light from red to blue, let's say you get shorter wavelength, higher frequency, well, now you do get energy. And in fact, everything past this threshold frequency, if you double the frequency beyond that, you get double the energy. And Einstein interpreted that as, well, the only way that would happen is if light also had particle properties. And the particles of light he called photons, and each photon carries a certain amount of energy. And the connection here is called Planck's constant. Right? And the formula basically is energy equals Planck's constant times the frequency, right? Beyond the threshold frequency. Right? Oh, so what we got now? Then De Broglie said, I wonder if other kinds of particles could have this duality also, beyond just photons and light. So it makes this connection where you can get the wavelength of any associated particle. Now, you guys know H is Planck's constant. That's like 10 to the minus 34. If you take that and divide by the momentum of a particle, you get an associated wavelength, which at the macro scale ends up being negligible. So does this 1 kilogram mass moving around have an associated wavelength? Yes, if you run this formula, but it's so tiny that you wouldn't really be able to measure it. Right? But if you have a small enough mass particle, say an electron, right, which did I tell you guys, I think a proton has almost 2,000 times the mass of an electron. So an electron is small, even compared to a proton. Okay? Then you do get a significant wavelength. And that actually explains all of chemistry. Why is the entire periodic table organized the way it is? Does any chemical reaction happen or not happen? Right? Why do valence electrons take certain places? Right? Because electrons can only fill certain orbital spaces around the atom. And the only explanation for that is this wave property of electrons. Right? So now we have this dual nature of particle, wave, matter entering into electrons. Okay? That's going to explain all of chemistry, and that's going to lead to the next one. So just to pick one specific example and run with it. Why are certain materials transparent, such as glass?
What makes glass transparent? Why can light get through this? Yeah, I've found a number of interesting and disturbing websites, I guess wrong answers, disturbingly wrong, in that they explain it in terms of, well, glass is like a liquid, and the molecules don't pack as tightly as they do in a solid, and therefore there are gaps in glass that the light can get through. That is wrong. Badly wrong on so many different levels. Yeah, so what is going on is it's with glass compared to other materials, the important thing is how the atoms are arranged in the solid. And how the atoms are arranged dictates, and this is the really important bit, how the electrons are arranged. And it's how those electrons stack up in different energy levels, or the energies of those electrons, that dictates whether light can get through. Right, so what I'm going to do now is I'm going to pretend to be a photon. I'm going to move through this room, and this room represents a substance, lots of atoms, electrons dotted around everywhere. So I'm moving through with a certain amount of energy. And my job as a photon is actually to take one of these electrons from its ground state, its lowest energy state, move it up and bring it up to a higher energy level. And when I do that, basically my job is done and I'm absorbed and I don't make it through the solid. So if it's brick, for example, this is what happens. The photon comes through, it takes an electron from the ground state, moves it to a higher energy level, is absorbed, doesn't make it through. The substance is opaque. For glass and other special materials which are transparent, Instead of what happens is that the difference in energy between the ground state and the high energy level, which we call the energy gap, is much too large. And as a photon, I'm coming through, what I need to do, or what to be absorbed, what I need to do is actually take one of these electrons and bring it all the way up here to this excited energy level. But I don't have enough energy to do that. I simply can't get it up there. So therefore, I'm not absorbed and I pass through the material. Getting out the other side, and so the material then appears transparent. So the energy difference between the ground state and this level, the difference between those two we call an energy gap. And an electron can only either be here or here. It cannot exist in between. We cannot excite it. So the photon gives up that energy and transfers it there, and then it's the photon basically is dead. So when it comes to glass and diamond and other transparent materials, that energy gap between the ground state and that excited level is so large that photons of visible light, photons with visible wavelengths, photons that we can see, have not got enough energy to actually get it from here all the way up there.
All right, there you go. All right, so guys, what's glass mostly made out of? Glass is mostly made out of, sand. Okay, and that's mostly silicon dioxide. Right now, maybe some other couple of things there too. There's different kinds of glass, different things you can mix in it. But let's say it's sort of a molecule of silicon dioxide, which would really be a silicon and a couple of oxygens. Okay, you got this electron cloud sort of collectively going around that molecule, right? This electron cloud. Okay, and if you look at individual electrons, well, remember where we left off last week was that electrons can only fit in certain orbital locations. Okay, so any particular energy gap you have here would be too large for photons of visible light to move the electron from one level to the next level. So here, I'll spell that out. Got energy gap is too large for photons of visible light to be absorbed. So they just pass through. Okay? And then anything that's opaque, like the walls here, why can't we see the classrooms going on around us? Okay? Is because photons of visible light, say, run into these electrons and actually do bump them up to the next energy level, right? So they would get absorbed, and then maybe that radiates off as thermal energy. But okay, and notice I'm saying visible light here, specified visible light, because that window and that door right there. Okay, we can see through the window, made out of glass. But what about other parts of the EM spectrum? Guys, is that glass right here? Does this glass block ultraviolet? Yeah, right. Because if you go on a road trip, do you have to wear a sunscreen if you're driving across the country on a road trip? Inside the car? Yeah. So you're safe inside the car, right? How about infrared? Does glass block infrared? Yeah, glass also blocks infrared, but just the visible part of the spectrum, those photons pass through. All right. So this next one, just set of back of these. Okay. What is the wave function, Schrodinger's equation? What is this?
Let's talk about quantum physics. What is quantum physics? Quantum physics is what happens to physics when we give wave properties to matter. So matter no longer is allowed to sit in just one place, like object sitting there. We've got to have it spread out like a wave. And that's why we call it given wave properties to matter. All right, so it's described by something called a wave function. All right, and so that's going to take the place of a position, a momentum, and all those things. Instead of that, we describe the behavior of a particle by its wave function. The wave function satisfies something called Schrodinger's equation, which kind of takes the place of conservation of energy. You can think of it that way in quantum mechanics. All right, so if we leave the particle alone, it behaves like a wave. So we're just sitting there, letting the system do whatever it wants to do, and it's described by its wave function. However, if we perform a measurement, suddenly we get something called the collapse of the wave function. So for example, if we've got a wave function that looks like that, and then we perform a measurement and we say, is the particle between these two green lines? Well, I mean, we're performing a measurement. It either is or it isn't. So it doesn't get to say, oh, part of me is there and no, it doesn't get to say that. We're performing a measurement. We're asking, is it or is it not? It cannot be both. And that is going to give us a probabilistic interpretation from quantum mechanics. So the wave function will give us probabilities. It'll say, all right, if you did that measurement 100 times, 6 times you're going to find that it was between the green bars, and the other 94 times you're going to find that it wasn't. Now, really a strange duality going on there. Because if I were to leave it alone, it's kind of like part of it's in between and part of it isn't. But if I do the measurement, then it either is or isn't. Whole thing is or whole thing is not.
Ooh. All right, so here's what this equation looks like. Actually, there's different variations on this equation. So there's a time-dependent version and time independent version of this. All right, so are you looking at a snapshot, or are you letting the clock roll forward and create a whole animation out of this? So what does this mean? And what this means is, if you're looking for the location of a tiny particle, say an electron on that side, okay, then it's going to exist probabilistically. So here I got graph probability versus location. Now this is a simplified 2D cross section of this. But actually it's a pretty good 2D representation. Okay, so say you don't have a single electron, but maybe you have thousands of electrons. You keep measuring over and over and over, and any individual one, it's going to look random. Like why is it popping up there? Why is it popping up there? But if you aggregate the data for thousands of electrons, then it creates a curve like this. And then you stand back and look at it and realize that, oh, I have a probability curve. Okay? And hey, look at like these peaks and valleys. It looks like there's special locations that the electron really likes to be. Oh, that kind of reminds me of these last couple of quadrants. Right? There's certain energy levels that the electron really prefers to be, and it doesn't really want to be in between. It looks like these valleys right here. Okay? Also, this is one of the reasons that I wanted to lead into quantum mechanics with statistics, because you guys remember that normal distribution curve? Does that normal distribution curve from a week or two back, kind of like that, sort of like that, right? And now here's just a kind of a fancier version of that, right? Like that. Okay. Now, so I can say that particles exist probabilistically as a function of location, right? But here's the weird catch too, is that measurement or observation, like use the terms measurement and observation interchangeably today, okay, causes the collapse of the wave function. Okay. So if I was making a measurement, like is the electron between these two lines right here? Here, I'll hatch that in. Okay. Say if I have a detection device, okay, measuring, is it right? Either it is or it isn't. Now the area under that curve, I'm gonna estimate, let's call it like 10%. So let's say there's a 10% chance that it is. Okay. So again, if you measure thousands of electrons, 10% of the time it'll be in that hatched in area, and 90% of the time, well, it'll be somewhere else. Okay. But once you make the measurement, and suppose that again 10% of the time it shows up there, that collapses the entire wave function, and then this whole thing recenters on that new location. So 1 nanosecond later, this peak has now shifted over to the location that the electron was exactly measured to be in, and this whole thing starts over. Okay. And then if you use the time-dependent version of Schrodinger's equation, then you can make an animation out of this. So as time moves forward, of course, the electron could be like more spread out. So then this curve gets like flatter. Okay. And then you make another measurement, and then bam, it collapses to that location. And then over time, it spreads out. And then you measure again, and bam, it recenters on the new location that was measured to be. That's why. All right, so you guys go with Schrodinger's equation? Let's do Heisenberg.
Today, I'm doing an experiment that demonstrates Heisenberg's uncertainty principle. So here I have a green laser, and I'm firing it down towards the front of the room through a narrow slit. Now that slit can be adjusted, so it could be made narrower or wider. And the laser spot is projected onto a screen behind it. So what do you think is going to happen to this spot on the screen as I narrow the slit? Well, let's have a look. You see exactly what you'd expect. The spot gets narrower and narrower. The sides are getting cut off by the slit. Makes complete sense. And if you stop there, you would never realize that Heisenberg's uncertainty principle is at work. But if you keep going, something strange happens. As you make the slit even narrower, the spot starts to spread out. Isn't that incredible? You're making the slit narrower, and yet the spot on the wall is getting wider. The narrower you make it, the wider that spot on the wall becomes. To understand this, we have to look at Heisenberg's uncertainty principle. Heisenberg's uncertainty principle is normally written as delta x delta p is greater than or equal to h on 4 pi. So what does this mean? Well, it's about the position and the momentum of a particle. So x is the position of the particle and p is its momentum. So delta x is the uncertainty in position and delta p is the uncertainty in the momentum. Now, if you multiply those two quantities together, they must always be greater than or equal to h on 4 pi. Now, h is Planck's constant, and that deserves a video all to itself, like this one by 60 symbols. But for our purposes, it's just a very small number. So in our everyday lives, we don't come up against this uncertainty relation because everything is much, much bigger than h. But as we narrowed the slit, we were decreasing delta x for those photons. So we were getting more and more precise about where the photons were passing through that slit. And at a certain point, you come to this limit, so that if you narrow this any further, you're going to break this uncertainty relationship. So what needs to happen is the uncertainty in momentum needs to go up. I should specify this is uncertainty in momentum in the x direction, in the horizontal direction. So if before photons were going perfectly straight, now they must veer off to the left or to the right to ensure that we don't break Heisenberg's uncertainty relation. And the more you decrease your uncertainty in position, the more narrow you make that slit, the more the uncertainty in momentum has to go up. And so if these photons are going to the left and the right, that's going to produce a much wider beam. It's really, really non-intuitive, but it's the way the world works.
All right, so that's this experiment, just a single slit experiment. You shine laser light through, so it's a bunch of photons. Okay. Yeah, what starts off is, okay, we got a band on the back wall, right, all fine and good. Right. He makes the slit narrower, narrower, narrower. Now, at first, the band on the back wall also gets narrower too. That makes sense, right? So classical physics makes sense, right? But if he makes that that gap too narrow, now suddenly that band on the back wall starts to spread out. And if you look really closely, it's looking more kind of like a wave pattern too. So it's sort of an interference pattern looking at this single slit. Okay? And so Heisenberg's uncertainty principle goes delta x times delta p is greater than or equal to h on 4 pi, about like that. Okay? Where delta x is the uncertainty in position, your delta p could be the uncertainty in momentum. And h on 4 pi, well, you guys know what h is. That's Planck's constant. So it's like 10 to the negative 34. And if you divide it by 4 pi, well, no, you just make it smaller, but it's still a constant. So I'll just call it a tiny constant. Okay. So small that in everyday, just macroscopic world, you never really tend to run up against this, right? But right, if you get extreme enough, so he makes this slit narrow enough for these particles of light, these photons, right? Well, now you're running into limitations about your knowledge of the universe, and this isn't something that you can't know because if only we had the detection equipment that was enough, then we would be able to measure it. No, this is like fundamentally part of the universe, a limitation on how much you can know. Right? So once you get that band too small, right, this gap here is too small, then you have too much certainty in position, which means the uncertainty of momentum, which is going to manifest this direction in this case, has to increase to balance this equation. Okay? So it has to be at least as small as this tiny, tiny number right here. Okay? One application I've heard of this has to do with, say, like Star Trek beamer technology. Suppose you want to beam yourself like on Mars or something, right? Say, well, how would you do that? Well, what if, could you, in theory, have some giant supercomputer that can map every single atom in your body and just replicate it somewhere else? But one of the problems you'd run into would be exactly this right here. Can you map the exact location? Can you have the exact knowledge for every single atom? Well, maybe not if you're running into Heisenberg uncertainty principle. Okay. By the way, that's if you watch Breaking Bad, that's why the character was named Heisenberg, because that was representing the uncertainty in his character. Ooh, you guys ready for a crazy one? All right, it's crazy time.
And here we are, the granddaddy of all quantum weirdness, the
Granddaddy.
infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing.
All right, so all he's doing right now, all he's done so far up to this point is just map out the definition of a particle and the definition of a wave. Right? If you fire particles through, you'll see individual bands. If you fire waves through, those waves are going to interfere with each other and give you an interference pattern. So now we know what is a particle, what is a wave.
So when we throw things, that is matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. The electron is a teeny tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition.
All right, so actually maybe that's not even super crazy based on some of the quadrants from last time it started today. You guys know that electrons have wave properties. Actually, electrons are probably better described as being waves than particles anyway. So maybe that's not super crazy. The really crazy part of this is everything after this.
With each other. But physicists were completely baffled by this. So they decided to peek and see which slit actually goes through. They put a measuring device by one slit, see which one it went through, and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act different, as though it was aware it was being watched.
Ooh, spooky. So here's the setup. All right, we got a card with a couple of slits in it, it's double slit. We're gonna fire through small particles. So here I have electrons. I think he was saying electrons. There's another version of this with photons, but the idea is that we're firing some small particles through. Okay. Now without the observer, or a measurement device. I'm going to use the terms observer and measurement interchangeably, but it's some way to detect something. Right? Then what do you get on this back wall? Well, you get an interference pattern. So sketch out an interference pattern right there. Right, so interference pattern, which would indicate that it's a wave or has wave properties. Okay, so maybe not super surprising, right? Based on, you guys remember like all this electron configuration from last week, that makes sense. But if you do have a measuring device, I'm going to represent that with a cartoon eyeball, just like he had to. I'll call this observer. Okay, so with the observer, it behaves like a particle. Okay. The interference pattern collapses and you just go back to having the two bands. Okay. So why would that be? And what implications does that have for the universe? One of the questions this opens up is, well, does the universe require some kind of consciousness to exist at all? But like, could you have an empty universe that just had a bunch of asteroids floating around with no consciousness, or what would that mean? What if there's an empty room and no observer, and like no security camera? Does anything in that room exist? Or what are we talking about here? Now, there's different variations on this. I'm going to play a part of a bonus video I have for you guys. Is what if you take that detector, like this is observer or measuring equipment? What if you put it like halfway between? And what do you guys think happens? Because if you move this observer from the point of the two slits to like halfway in between, where the particles have already passed through and they're already in motion, do you think you keep the double band, or do you think it turns back into a wave? What do you think? Okay, here, show of hands. What do you guys think? Suppose I put this measurement device like halfway. How many of you guys think it collapses back to a wave, or turns back into a wave? Okay. How many of you guys think it stays as a two band? Okay. Yeah, it turns out it just stays as two bands, which has a really weird application too. Because remember, if you have no observer at all, it's a wave. If you have the observer here, then it collapses to a particle. But even if you move the observer here, it still stays as a particle, which maybe implies that it retroactively became a particle. Like how does that even make any sense? And that version is called delayed choice quantum eraser.
All right, you ready to have your minds blown? Oh man, your minds are gonna be blown big time.
So here, I'm just gonna pause this here. So this is the more technical version of this. I know the cartoon version I played had that cartoon eyeball floating, but I mean, in reality, what does that really mean? So here's a more proper setup. Right? So here's your laser, you're firing a bunch of maybe photons. Here's your card with a couple slits, slit A, slit B. Right? And then, well, you can have these photons go on some journey until they eventually reach this coincidence counter. And depending on how they get there, you'll either get bands or an interference pattern, which would indicate either particles or waves. Okay. Now, some days like here, like this top one, which came from here, well, could have traveled either through A or B, right? So if it goes through A or B, maybe either way could end up here. So now you have some ambiguity, and you always get a wave pattern, right? But if you follow some of these lines, you could say, well, it only came from, say, A, if you follow this pink line, or something like that. Right? So you get bands, so you can know, right? And again, that's true even if the detector is like beyond these two slits, right? So Alright, so I'll leave that there. Let's go on to measurement problem and Schrodinger's cat. Ooh.
But despite gravity's unwillingness to fit in with quantum theory, I believe there's something worse lurking in the quantum shadows, something truly nightmarish. Late into the night at physics conferences all over the world, over drinks at the bar, when we scientists huddle together to debate and discuss our strangest ideas and dreams, there are still things that really, really bother us. And chief among these are the quantum mechanical laws that atoms obey. And in particular, one aspect of these laws, something called the measurement problem. If you want to see fear in a quantum physicist's eyes, just mention the words, the measurement problem. The measurement problem is this: an atom only appears in a particular place if you measure it. In other words, an atom is spread out all over the place until a conscious observer decides to look at it. So the act of measurement or observation creates the entire universe. And just to show you how mad this idea is, I'm going to explain one of the most famous hypothetical experiments in the whole of science. It's called the Schrodinger's cat experiment. Erwin Schrödinger was one of the founding fathers of atomic theory, and in the mid-1930s devised a thought experiment purely to highlight the absurdity of quantum mechanics. He suggested you take a box in which you place an unopened container of cyanide connected to a radiation detector and some radioactive material. Now, the idea is that if an atom in the material emits a particle, this will be picked up by the detector, which in turn releases the cyanide. Next, you take Schrödinger's cat, which in this case is a lovely Norwegian forest cat called Dawkins. Now, I should point out that this isn't real cyanide. You place the cat in the box, you close the lid, and wait. So here's the conundrum. According to traditional quantum mechanics, known as the Copenhagen interpretation, all the time the box is closed, the radioactive atom inside has yet to make up its mind whether it is decayed and spat out a particle. So we have to describe it as both having decayed and not decayed at the same time. Think about what this means. Since the radioactive particle triggers the release of the poison, the cat is both poisoned and not poisoned. So until we open the lid to check up on the fate of the cat, what's called making a measurement, it's not just that we don't know, but that the cat is literally both dead and alive at the same time. This is clearly a paradox, or is it? The paradox of Schrödinger's cat and the contradictory nature of the measurement problem really does force us to accept that tiny objects down at the atomic scale obey their own set of profoundly strange rules. But at larger scales, those of everyday human experience, those rules vanish, and an utterly new set of nice, intuitive rules take over. How can this be? Some argue that in fact, the quantum weirdness of the atom might actually be writ large across the cosmos, that we may have to rethink everything we knew about the universe.
Ooh. All right, so here's the setup. Got a closed box. A closed box. All right. When I say closed, I mean that there's no way any outside observer could know what's going on inside. So I'll draw an eyeball to represent some outside observer here. Label this guy observer. Right. But the observer cannot see inside the box, can't feel inside the box. There's no way to detect anything inside the box, right? As long as you got it closed. Okay. All right, here I got a radioactive particle. So I got radioactive particle in a state of superposition. Remember back to Schrodinger's equation is that down the atomic scale, atoms exist probabilistically. Okay? Now, radioactive, there's different kinds of radioactive atoms. Some atoms are radioactive, they have a half-life of like a nanosecond, so they decay pretty much immediately. Okay, and some have a half-life of thousands of years. So if you start off with like 10 grams of the material, after say like 1,000 years or so, right? Now you're down to 5 grams. And after another 1,000 years, maybe you're down to like 2.5 grams. Right? So it takes some time. Okay. Let's say this has a half-life of like an hour. So we'll put this radioactive particle in the box with the poison and the cat and close it, and we'll come back in and check on it in an hour. Okay. Now, if that radioactive particle does decay, which 50-50 chance after an hour, if it has a half-life of an hour, okay, this is gonna trip this this poison. So radioactive decay trips the poison. Okay. Hence, it would link the quantum world to the macroscopic world. Right now, we have some connection here. But here's the problem: is that, or the conundrum is that if the radioactive particle, whether it's decayed or not, is not binary, it's probabilistic, okay? Which means that this whole process is probabilistic. So whether the poison has been tripped or not, well, maybe "or" is the wrong word, right? You can only describe it probabilistically. So you can say, oh, well, after 1 hour, there's a 50% chance that it has been. So it's in Sator's superposition where it's both tripped and not tripped. Okay? Which means then that this cat right here, cat, is in a state of superposition. It's both dead and alive. Okay. As long as the box is closed. Okay. Now, of course, once you open the box, you're making an observation, you're making a measurement, and then that collapses the entire wave function to just one or the other reality. And now you're back to binary. Right? So you're the cat is alive or dead at that point. Okay. I think you guys probably caught too. This is a Schrodinger thought experiment. At the time, he was looking at a bunch of results from quantum mechanics and say, these results are so absurd, there's no way this could actually be true because, and then he came up with this thought experiment. But then people connected onto this and said, actually, you know what, that is a really good idea. This does say something weird about our universe. Right? I mean, what's the other implications of this? Like who's inside what box? I've heard an extension of this. It's like, is everyone on Earth inside a closed system box? And like, what are we to like some aliens of some other galaxy? Okay. So what implications does this have? Kind of hard to come up with an experiment to know for sure, because once you make an observation, it collapses it to one or the other state. Okay. Why haven't we done this? Because it'd be sort of impossible to do. Because like once you have some detection equipment, like either the cat's alive or dead, it skips straight to this. Like once you have any kind of knowledge, it skips to being binary, one or the other. Okay. Like the idea of like it being in the superposition of like being both dead and alive simultaneously, that's before you ever make any kind of measurement or any kind of observation. Right? So it's during the point where the box would be closed and there's just no way you can know what's going on inside. Right. Yeah. I mean, you could do this, but the outcome would be really predictable. So if this album had a half-life of 1 hour, suppose you had 1,000 boxes with 1,000 cats. Yeah, 1,000 cats, right? And you run this experiment 1,000 times. Well, probably about 500 times the cat's alive and 500 times the cat's dead, right? That could be predictable, right? But what about the intervening hour, like up until the moment that you open the box, right? And there's just no way to know except to have this thought experiment to think about it. All right, let's do one more. Quantum Zeno.
I've had a long, annoying day at work, running from one committee meeting to another. I come home with a pounding headache. I have an hour or so until Kate gets home, and all I want is a nap. Emmy is ecstatic to see me and does the happy dance all over the living room. Hooray, you're home! Yippee! She's wagging her tail so hard she almost loses her balance. This happens every afternoon when I come home. It's good to see you, too. Let's do something fun. Let's play fetch. Let's go for a walk. Let's play fetch on a walk. Let's let me take a nap. She stops bounding immediately and looks crestfallen. Her ears and tail droop. No walk? Not right now, I say, lying down on the couch. Let me sleep for half an hour and then we'll do something fun. Promise? I promise. Now be quiet. The sooner I get to sleep, the sooner we'll do something fun. Okay. I lie down and get comfortable on the couch. I'm just starting to settle in for my nap when a cold, wet nose pokes me in the face. Are you asleep? No, I'm not asleep. Oh. A minute passes. Poke. Are you asleep? No. Another minute passes. Poke. Are you asleep? No. I sit back up, and I'm never going to get to sleep if you don't stop poking me with your nose and asking that question. Why not? Every time you poke me, you wake me back up. I have to start over again. You keep waking me up, I don't get all the way to sleep, and you don't get to do anything fun. Oh. She brightens up. Hey, it's just like the zero effect. The what? You know, the paradox with the guy who can't catch the turtle because he has to go half the way to the turtle and then the next half of the way and then so on. And so he never gets anywhere. You mean Zeno's paradox. Zeno with an N as in nap. Zero Effect is a movie with Bill Pullman and Ben Stiller. Whatever, I don't spell so good. Anyway, what you're thinking of is the quantum Zeno effect. And yes, this is kind of like that. If you have a system that's moving from one state to another with the probability of being in the second state increasing over time, you can prevent the state change by repeated measurements. Every time you measure it to be in the first state, you restart the process. Right, so when I ask if you're asleep, I collapse your wave function back to the awake state, and you need to start napping again. Or you find yourself perceiving the branch of the wave function in which I'm awake again in the many worlds picture. But yes, that's the basic idea and a good analogy. I'm a philosophical dog.
Philosophical dog. So the graph they flashed up there. Okay, so we're back to this radioactive atom. Okay, so hey, maybe kind of like the one the Schrodinger's cat thought experiment, okay, where maybe it has a half-life of an hour. Just throw a number at it. Okay. So if you let a few minutes go by, maybe low probability is decayed. But if you let an hour go by, that should be up to 50%. And then after another hour, be another 50%. So now we're up to 75%. It should be decayed after a couple hours, and so on. Okay. Should asymptotically approach 100%. Okay. But here's the conundrum: is that with continual observation, the wave function continually collapses to its original state. So radioactive decay never happens. If it was a half-life of 1 hour, if you checked only every hour on the hour, then every hour that passes, there's another 50% chance that it's decayed. There'd be 50%, 75%, 88%, asymptotically approach 100%. Okay. But if you keep the detection equipment on it, say every nanosecond, so just continual watching it, okay, then that Schrodinger equation from earlier today, you guys remember the Schrodinger equation? It keeps collapsing back to its original state. Okay, so hasn't decayed, hasn't decayed, hasn't decayed. Okay. Now, after like 10 hours, you say, well, it's like 99 point something % chance it should have decayed by now. Great. Another 10 hours, another 10 hours. Say, oh man, I'd have a better chance of winning the lottery than it hasn't decayed by now. Why is it not decaying? Okay. Well, because it's this quantum Zeno effect. It keeps collapsing the wave function back to its original state. Okay. Again, going hand in hand with this measurement problem, Schrodinger's cat, this double slit experiment. There's some kind of connection between observation, measurement, and reality. Okay. All right, and that is our pause point today.